Hi, I'm Scott Niekum. I'm an assistant professor at the University of Texas at Austin. And today I want to talk about providing probabilistic guarantees on the performance of imitation learning algorithms. So, whenever people say safety or correctness or high confidence, it's not always clear what people mean. So, I'm just going to give a definition that I'll be using today, which is that when I say safety, what I really mean is correctness plus confidence. So, correctness can be really meeting or exceeding any measure of performance, whether this is, some minimal amount of return you want to get in a reinforcement learning problem, or meeting certain temporal logic constraints, for example. Confidence is just having a probabilistic guarantee of correctness. And so being highly confident that our behavior is correct. Okay, so one of the high-level goals of the robotics community is to get robots into people's homes and workplaces, and there are just far too many tasks in different environments to have experts sort of pre-program robots to do everything a person could possibly want a robot to do. And so one of the tools we use is imitation learning, where we show demonstrations to robots of what we want them to do, and it's a nice way for end users just to be able to program robots. But unfortunately, the sort of current paradigm of learning from demonstrations in this way just says, well, take the demonstrations, throw them at our favorite imitation learning algorithm, close our eyes, cross our fingers, and hope it works. And that's obviously not going to be acceptable to end users if often their robot does the wrong thing. So we want robots to be able to tell their users whether they're confident or not that their values or their performance is aligned with that of what the person really intended for them to do. So how do we do this? This is a challenging problem. So more sort of mathematically, what we want to do is upper bound the policy loss, the difference between the value of the expert's policy, pi star, under the true reward function, minus the value of the robot's policy. And we want to bound that within some epsilon with high confidence, probability 1 minus delta. So we're upper bounding the policy loss of the robot versus the human demonstrator with high confidence. And the trick is, we have to do this without knowing the ground truth reward function. That's the hard part, is that we only have access to the demonstrations. And so we kind of need this, theory of mind a little bit, where the robot has to think about, well, given what the demonstrations that were shown to me, what's the probability distribution over the different things the person could have meant? And then what's, my performance with respect to that distribution? So this is much harder than what's often called the safe reinforcement learning problem, or high confidence, policy evaluation, where we're trying to evaluate a policy, but with respect to some reward function that we know. Here, we only have access to the demonstrations. So this is a really challenging problem. But what I want to be able to do is just give a bunch of demonstrations to the robot, and then have it think for a while, come back with a policy, basically, and tell me either, hey, I think I am almost as good at this task as you are, or I'm not, and I need more demonstrations. Okay, so we're going to need some tools to do this. So just a sort of primer on inverse reinforcement learning, if you haven't seen this before or have forgotten. So going back to the original IRL paper from Abil and Eng in 2004, what we're going to do is we're going to assume that without loss of generality, that our reward function can be expressed as a linear combination of features of state, phi. Those features themselves can be nonlinear functions of state, though. And so our reward function here can be parameterized as just a vector w, so that our total return that we get is, or the reward we get in a state is w dot the features of that state. And so then the expected value of a particular policy pi over a starting state distribution d can be written in this way. And we can just pull the weight vector w out of the expectation so that we get w dot an expectation over the discounted features we're going to see when we run policy pi. And we're going to call those discounted feature expectations mu of pi, okay? And the goal of IRL in this framework is to find a reward function whose optimal policy has feature expectations that match the experts. Why is that? Well, because if we match the feature expectations, since reward is linear in those feature expectations, then the expected return is also going to be identical. And in this work, Abil and Eng were able to show that, and actually there's a tighter bound that we're showing here from Syed and Shapir in 2008, that if we bound the one norm of the weight vector, then we can pretty easily bound the policy loss So the policy loss can just be bounded by then a difference, because we're trying to match the user's feature expectations. They can be bounded by a difference between the expert's feature expectations and the robots, which are going to get multiplied by the weights that represent the reward function. And further, we can bound this, because we're bounding the vector w, to the infinity norm of the difference between these. So you can interpret this as a worst case bound. You say, well, whichever feature we're kind of doing the worst at matching, imagine all the weight of the reward vector goes on that feature and is penalizing us maximally for not deviate, or for having deviated there. Now you'll notice this bound, it assumes that we know the experts' expected feature counts exactly, which we don't. We only have access to demonstrations. So there's, to bound this with high confidence, so probability 1 minus delta, we need to put a concentration inequality, or like Hufting style bound on this. And so they have a bound that shows that there's some number of demonstrations m that are sufficient for bounding this within epsilon with probability 1 minus delta. Okay. And unfortunately, in practice, this number m, even for very simple problems, is just enormous. You need tens of thousands of trajectories or something for really simple problems. So, and this is the only other work we know of that has really tried to address this problem of bounding performance. So can we do better? And yes, we can. And to do so, we're going to challenge this assumption, the assumption that worst case reasoning is the best we can do if we don't know the ground truth reward function. So worst case reasoning is a little weird, right? Because if I show you some demonstrations where I say, not where I say it, but where I show you that I almost never, never step in lava, I always eat food, it would be weird to say, well, I've learned this policy and I think it's pretty good, but it could be really bad if what the person really meant is that lava is good and food is bad, right? That seems like very strange reasoning. And so what we're going to do instead is we're going to gain a lot of efficiency by considering the likelihood of reward functions when assessing risk in a Bayesian framework. So before I get to our method of how we do this, we need a couple more tools. So one of them is this idea of Bayesian inverse reinforcement learning. So the idea here is that instead of getting a point estimate of what we think the reward function is, we're going to use MCMC to actually generate samples from the full Bayesian posterior. And if we just assume a uniform distribution over reward functions for now, then our posterior of R given D is just going to be proportional to the likelihood of the demonstrations given a reward function. So given any particular reward function that we would sample during MCMC, the likelihood of the demonstrations then under that is just going to assume Boltzmann rationality, or it's going to look like this kind of softmax. What it's basically saying is you have some temperature parameter C that sort of controls how optimal you think the expert is. And we have to compute Q star, which is very expensive. We're going to get rid of this assumption that we can compute Q star later. But we want to compute Q star with respect to this reward function that we're being given. And to compute the likelihood of the demonstrations, we're saying that we're assuming that the demonstration should be good with respect to that reward function. In other words, we should be taking actions with higher Q star values compared to the other alternatives at that state exponentially more often than the worse alternatives, essentially. And we can use that to then determine the likelihood of each reward function, which we can use to decide whether we accept our MCMC step or not. And this gives us a bunch of samples of possible reward functions that could be true given the demonstrations. We need one other tool, though, so that we can consider risk. And this is a tool called value at risk that is often used in communities like finance. And it's a statistic that we look at over the CDF, the inverse CDF of some distribution. And so what it essentially is a cutoff. So you want to be able to make a statement in like finance, for example, where you say, well, based on historical data, if the historical data holds true, but when I use this investment strategy, I won't lose more than $500 more than 5% of the time. And so what you do is you set some percentile alpha and you say, how bad is the cutoff between the best 95% of cases and the worst 5%? And that's the value at risk, okay? There are other measures of risk. So there's things like conditional value at risk that looks at the mean of those tail cases instead of the cutoff, but we're going to use value at risk here. You'll notice, though, that value at risk does not take into account the number of samples you actually have from the distribution. And so if we want to know a metric of risk that has sort of a confidence associated with it, we also have to put a single-sided confidence bound on it. And so that's going to allow us to make statements along the lines that of something like this, with probability 1 minus delta, no more than 1 minus alpha of the outcomes will be worse than X. And if we, choose delta to be something like, 0.99 and, alpha to be something maybe like, 0.95, we can just solve for X and we can check if it's below some acceptable level of risk or not. And so this is going to allow us to do essentially what we want to do now. We're going to be able to make statements, and I'll show you how in the next slide, how our algorithm works, that with high confidence, probability 1 minus delta, most of the time the robot can guarantee it's going to do at least within, some fraction of how well the human expert performed. And if those numbers, represent a risk that is acceptable to the human, then we're done. Otherwise, the robot needs to see more demonstrations before it is convinced that it can perform almost as well as the human in a task. Okay, so here's how our safe IRL pipeline works. It's going to be making some big assumptions about either having sort of an MDP solver or a model, or at least a lot of samples. We're going to relax some of these unrealistic assumptions later, but I just want to present this framework first. So we get some demonstrations from the user or the expert, and we perform Bayesian IRL, meaning that we're going to run MCMC, and it's going to give us a whole bunch of samples from the reward posterior, given the demonstrations. We're going to take the map, or the maximum a posteriori sample, and we're going to say that we think, that's the sort of most likely reward that we're going to go with, and we're going to solve for pi star with respect to that, okay? And we're going to call that pi star map. That's the policy that the robot is going to run. There are other choices that we could make for the policy the robot wants to run, but let's just go with that for now. And then for every other reward function that we sampled during the MCMC chain that could have been true, we're also going to solve for the optimal policy for that. This is obviously very expensive. Okay, then what we're going to do is for every one of these reward functions that could have been true, we're going to compute a policy loss that says, well, we computed this policy that we're actually going to run with respect to our map, but what if we were wrong? What if some other reward function Ri was true? Okay. So if it was true, what we need to do is compare how well is our policy that the robot's going to run going to do on some other reward function Ri compared to the policy that's actually optimal under Ri. And that's going to give us a whole distribution of policy losses, right? And we can sort them, compute the value at risk, this alpha cutoff, and we can put a single-sided confidence bound on that. And that's going to allow us to make these probabilistic statements that say, well, hey, I'm pretty sure that most of the time, I'm going to be within this level of, within like this epsilon of performance of you, even though I don't know what the true reward function is, or I'm not going to. And, as the robot, I need to see more demonstrations. So the robot can either just blindly ask for more demonstrations if it needs them, or we actually have a couple papers on both an information theoretic criteria or a risk-based criteria to actively query in an efficient way. So that's the pipeline. So before we look at how to actually make this more efficient and sort of, more usable in the real world without having to solve for all these optimal policies, let's just take a look at some quick results. So we don't need to get too into the details of this table, but this is just for a simple grid world problem. If we look at R bound compared to the most efficient other bound that we know of, that Syed and Shapir one I showed earlier, you'll see that we can get the same tightness in our bound with a single demonstration as the Syed and Shapir method is able to get with 23,146 demonstrations. So at least on this MDP, we are 4 orders of magnitude more data efficient because we're thinking about probabilities and likelihood of different reward functions and not just using worst case reasoning. And we can do this without violating the accuracy that we claim to be providing, which is 95% accuracy in this case. So this is really exciting. And to get a little bit more qualitative, maybe notion of what our algorithm's doing, if we show some demonstrations that look like this to the agent in this really simple car driving domain where the car avoids other cars and it has no lane preference, so it just kind of flits around, but it stays on the road, it doesn't go off-road. Then what we can do is we can show our algorithm 3 other policies, and we can ask it to rank them sort of in order of how risky it thinks each policy is, okay? And so in one case, oh, sorry, this video's not playing, but it's a policy that avoids cars but prefers the right lane. That's the safest one in reality. This one stays on the road, but it ignores other cars, so it sometimes hits into them, but it kind of flits around like this one did. And this one actually is the riskiest and actually seeks out collisions. And if we kind of ask the Seidensch-Peer method to rank these, we actually get a ranking that's almost completely backwards. It actually thinks this really good policy is the worst. Why? Well, because if you think about the feature counts are really different, right? It's spending all its time in the right lane, and it can say, well, what if being in the center lane and the left lane was actually really important? This could be really bad, whereas the feature counts here, even though it hits cars sometimes, look a lot more similar. Whereas our algorithm gets the ranking of risk right and reasons about it correctly because it looks at these demonstrations and says, well, the car really wouldn't be moving around in the way it is and unnecessarily spending so much time in the right lane if, for example, being in the left lane was really important. So we're able to reason about this correctly. Okay, so this is really cool. Even though we don't know the ground truth reward function, we can efficiently reason about risk. But the problem is that we still need this MDP solver. You know, we have this MDP solver buried in the inner loop. And this is just a problem with sort of inverse reinforcement learning algorithms in general, that you either have methods that have this MDP solver buried in the inner loop that solve for either optimal policies or value functions for every candidate reward function, or you have ones like generative adversarial imitation learning or GCL that kind of do this back and forth where they like update the discriminator or the reward function, then collect some policy rollouts, and they keep going back and forth. But in any case, you're collecting a lot of policy data at runtime. The other problem, though, with IRL algorithms is we often say that, you know, compared to like behavioral cloning, IRL is inferring the intent of the demonstrator. But I don't think this is really true because if the demonstrator makes a small mistake, for example, humans don't over-imitate that mistake, but our algorithms do because they often are just doing like feature count matching. And this is the critical flaw is that they're assuming the demonstrator is near optimal and they cannot outperform the demonstrator. And so I'm going to show an algorithm called TREX, which stands for Trajectory Ranked Reward Extrapolation, that fixes both these issues. And we're going to fix these issues by breaking this assumption that IRL should assume that the expert is near optimal. And instead, we're going to show that by having ranked, preference ordered, but suboptimal demonstrations, we can get significant computational and performance benefits. And here's how. The idea behind TREX is that if we see some demonstrations that are ranked in order of how good they are, what we want to do is essentially search for a reward function that explains that ranking. So if it's a state-based reward function, if we apply that to every state in a trajectory that's ranked higher should get more weight or more total return than one that's ranked lower, right? And hopefully what it will find, since we have a ranking we're trying to explain, is something that explains why these are ranked the way they are. So, oh, I see that, you know, as this gets better, the agent is stepping in lava less and eating food more. And hopefully that extrapolates to policy, to rank, being able to rank trajectories that are better than even the best one that was shown to the agent. And one really nice thing about thinking about learning this way is it's fully supervised. There's no policy learning or data collection that's needed to be done during inference. We can essentially just transform this into a classification problem where the amount of return that each trajectory is given under our state-based reward model can just be used in kind of a softmax kind of way to assign a probability that one trajectory should be ranked higher than another. So it's just a classification problem. There are no action labels required, so we can actually learn from just observations. We can extrapolate because of this suboptimality assumption of the demonstrations. And it turns out that it's the first imitation learning algorithm we know of that's doing reward inference that actually works on high dimensional problems reliably like Atari. And we can do this with about 10 demonstrations by getting creative with data augmentation. So here's some examples. In the half-cheetah domain in Mojoko, we see here's 3 suboptimal demonstrations we gave in progressive order of how far they get and how good they are. So kind of 2 face walks and an unstable walk. And we see the TREX is able to learn a coherent walk that extrapolates beyond the best performance of the best demonstration that it saw. Similarly, in Atari, here's the best demonstration we saw in Space Invaders. It gets a score of 600, and T-Rex is able to learn a policy eventually that is able to do more than get more than double the score by inferring a reward function and then using PPO on top of that to learn a policy. And across all, it turns out this is just two, but across a lot of different Atari and Mojoko domains, we see that T-Rex in green is able to significantly outperform the best demonstration that was given in blue, behavioral cloning from observation in red, and generative adversarial imitation learning in yellow. And just to give a sort of intuitive idea about what extrapolation looks like, if we ask it to tell us what they thought the worst and best frames were in Space Invaders, it thought the worst frames were this one where all the aliens were still alive, and the best frames were the ones where all the aliens were dead, even though during training it actually never saw a screen clear. And so it's able to correctly extrapolate the idea of kind of what goodness in this domain is to figure out that a screen clear is kind of the best thing that can happen. Okay, so one thing you may have noticed is that we've assumed so far that we actually have rankings being given to us, which is not a standard assumption really that's made in imitation learning. Usually you just have a pile of demonstrations and we assume they're near optimal. So we developed a version of our algorithm that is able to just take a pile of unranked demonstrations and sort of auto-generate rankings so that we can still use this nice idea from T-Rex that gets us so much efficiency and prevents us from needing to solve MDPs or collect any inference time data. And we call this DREX, which stands for disturbance-based reward extrapolation. So here's how it works. We take a bunch of demonstrations that are unranked and we just perform behavioral cloning on them. So in a fully supervised way, we learn this behaviorally cloned policy. Then what we start doing is generating rollouts of this policy. First, just normal rollouts. Then we start adding more and more action-wise noise to the trajectories as we roll them out, with the assumption that the more noise we add, in expectation, the worse it's going to perform until sort of we hit some threshold where we've added enough noise that it's performing as poorly as a random policy. And so we assume that this provides sort of a weak ranking over trajectories, that the ones with more noise in them are worse than the ones with less noise in them. And then we can just run those trajectories through T-Rex. And it turns out that in many domains, this performs about as well as T-Rex does, even if we have just a bunch of ground truth rankings. So now we can use the same idea, but in a scenario where we don't have access to rankings. And finally, we want to take this idea and we want to be able to plug it back into our safety work. Instead of having Bayesian inverse reinforcement learning, we want to be able to use something that looks like T-Rex that's much more efficient. But T-Rex only gives us a point estimate of the reward function, not a distribution. So we have a new paper that we have an archive version up now. It's also in submission. That's called Bayesian Rex. That is the same idea, but in a Bayesian form. And the basic way it works is that we take our ranked demonstrations or our auto-ranked demonstrations using that kind of DREX idea. And we first pre-train a network that's basically a feature extractor. And we do this by running just normal T-Rex to get a point estimate of the reward function, plus a bunch of auxiliary losses to make sure we get a pretty wide range of useful features. This is things like predicting forward dynamics, inverse dynamics, etc. Once we've pre-trained our feature extractor, what we do is we take all the ranked demonstrations and we stick them through our feature extractor so that we get a vector of feature counts for each of the ranked demonstrations. And we're doing this because we want to pre-compute this so it's really cheap for any given reward function, which is just a weight vector W, to just compute how much return each of these demonstrations gets, which we can do just by taking a quick dot product. So then what we do is we do MCMC and sample a bunch of weight vectors. We dot them with each of these, and we have basically a loss function that says that this weight vector, if it's a good weight vector, it should agree with the ranking, meaning that this trajectory should get more total return than this trajectory, etc. So we want to see essentially how many of these ranking constraints it's violating and how badly. And that gives us a probability, essentially, of the demonstrations given that reward function. And that's going to allow us to decide whether to accept the MC-MC step or not. And it's going to give us a distribution over reward functions just like before. And we've seen that Bayesian Rex performs about on par with T-Rex in general, and we're actually just learning a policy from it. But it also has this new neat ability of being able to reason coherently about risk, right? And so in this game, a game called Beam Rider, we hand created some policies A, B, C, and D that are better and better in increasing order from A to D. And we can see that by the ground truth score they get. And we also create this funny little no-op policy. So Beam Rider is this strange game where until you hit a particular button, the game doesn't start. It just kind of sits at a screen that looks like this. And the idea here is that one type of reward function that can actually explain this ranking very, very easily is that you'll notice that as the agent does better and better, it typically lives longer and longer. And so if you just give a constant reward per time step, you get a reward function that actually explains this really well. And the no-op policy lives very long, in fact, until the emulator times out. And so under the mean reward function in the distribution, it gets the ordering of A, B, C, D correct, but it also thinks the no-op policy is really good because it lives so long. Whereas if we look at the 5% value at risk that's thinking about risk, it realizes the no-op policy is really risky because maybe it's good just to live long, but maybe there are other features that are important too. And under that whole distribution, it realizes that no-op is very risky. So now what we can do is we can put this all together. We have this theory of safe imitation learning that was not efficient because we needed this inner loop policy solver or MDP solver. We showed a way to leverage this idea of preference-based rankings to do really efficient reward inference, and then how to turn that into a Bayesian version. And now we can plug it all back together, and we're trying to use that now to scale up to visual manipulation tasks. So we've actually kind of built this little robot setup on an air hockey table where we made sort of a physical version of the Atari game of Breakout that we're now scaling up to. Okay. I'm running short on time, but I just want to touch very briefly on a couple other things we're working on that are tied to this. So far, I've mostly talked about kind of statistical tricks that allow us to make imitation learning more efficient, but we're also exploring other avenues too, including new multimodal sources of data that can help us be more certain about what people's intentions are, ranging from auxiliary videos from sources like YouTube to natural language narration of demonstrations, to using human gaze to help us better infer what a person meant when they gave us a demonstration. And we have papers out on all of these. We're also looking at things like theory of mind. And so in a paper that I really like that we published last year, we showed that, if instead of just assuming that somebody's near optimal when they're demonstrating, we can also sometimes assume that they're near information optimal. For example, that they're going to give us a variety of demonstrations, or that they're going to try to show us the most informative demonstration, like that it's important not to carry the mug over top of the laptop rather than just kind of going straight there if that's what's important to them. And if you make this additional assumption, it turns out that you can get a lot more efficiency and disambiguation out of a small number of demonstrations. So we're exploring all these different avenues of being able to get as much efficiency out of our demonstrations as possible and provide safety and correctness guarantees in a probabilistic sense so that people can have confidence that their robot's going to do the right thing. So with that, I just want to thank my lab and all the students that have worked on these projects. And yeah, thanks for checking out my video.